Hello, I'm Isaac,
My name is Harry.
and we are proposing a solar cell monitoring system for use on GT Solar Racing.
As the team name suggests, solar cell performance is crucial to the performance of the vehicle. However, due to the arduous race conditions, solar modules may become damaged or degraded. To put it into perspective, the bottom right picture is the solar car being driven on I-25 from La Junta, Colorado to Las Vegas, New Mexico. As you can see, the solar modules are definitely not working under ideal environment, but rather coping with real-time situations. As a result, it's absolutely essential to understand the characteristics of the solar array under those effects to make a correct strategic decision. Currently, our solar array is divided into 3 zones, and it does provide a zone-level measurement. However, that's not the granularity that we want for a more accurate simulation of the array behavior. This is due to the fact that solar modules in different position of the array will have a different impact on the total performance. For example, a solar module at the very middle of zone 1 will have a much larger impact than a solar module at the edge of zone 1 due to cosine loss or the respective angle to sunshine. Another side benefit of developing this system is that it's much easier to debug which solar module is damaged or degraded, and we can replace them in time.
So, working back from our ultimate goal, we want to improve the accuracy of how we simulate our solar array. In order to do this, we must first measure the voltage, current, and temperature of individual modules, where modules are the smallest separable unit that our array can be broken down into. We want to use these measurements to automatically recognize deviations from their ideal performance and then adjust how we simulate accordingly.
So this is the architecture of our proposed solution. As you can see, it contains 3 main components: the solar car, the telemetry server, and the user's computer. For each solar cell pair, we will have a monitor board which will broadcast data through Bluetooth to the BLE receiver. The BLE receiver will then transmit those data to the telemetry server through LTE. The job of the telemetry server is to compute the IV curve, which is an important characteristics of a solar module, and detect deviation. When the deviation is higher than a certain threshold, we'll then alert the simulator to rerun the simulation with the latest solar array model.
To collect the measurements that we need, we are designing a custom circuit board which will measure the characteristics of 2 modules. We can install several of these into the card in order to measure the entire solar array. On this board, the main sensors are an analog-digital converter to measure voltages, a shunt current sensor, a thermistor to measure temperature, and a light sensor to detect shading. Tying it all together is the NRF528032, which is a system on a chip containing a Bluetooth low energy module that we will use to implement logic and output the measurements.
The next part of the proposed solution is the telemetry system. To explain what the telemetry system is, it's basically the trace the measured data will follow until further processing. From the NRF52 microcontroller on the monitor board, the data will be first broadcasted to a Bluetooth receiver, which is an ESP32 in our case, through Bluetooth. The ESP32 will then translate the BLE frame into a CAN frame, and it will send the CAN frame to the telemetry board. The telemetry board will then consume those data and upload the measured data to InfluxDB, which lives in the telemetry server through LTE.
Once we have measured data, our deviation recognition system will process it on the server. It will create IV curves from the measured voltage and current of each solar module. We can compare these curves to the shape of an ideal curve to detect damage. As is shown in the figure, a dent will appear in the curve of a module that's damaged, even if it is not shaded. And we can also compare other measured parameters of the module, like its short circuit current or its maximum power, to the corresponding datasheet specifications to further detect deviations from ideal performance. We can implement this logic through the telemetry server's computation system, which is an API that allows you to run calculations in response to incoming data points.
The last part of the proposed solution is the simulation inputs generation API. To take better advantage of the collected data, this API will produce a MATLAB file so that the MATLAB simulator can load instead of the ideal model that we're currently using. We're also going to create a wrapper program around the simulator so that it can be automated to call the API and rerun the simulator when there's new solar array model available. Also, there's assumption that if we only have one solar cell measurement unit, we'll apply the results to the entire corresponding array zone.
In order to evaluate the performance of our system, as a first step, we will perform basic tests of its functionality. For instance, ensuring that we can ingest measurements into the database and run computations in response to it, and we can do this using spare solar cells. Next, we will install the PCB into the solar car and perform extended drive tests over the course of several hours to gain evaluation data. If the larger solar car team's timeline allows, we will run our system at the mock race that is currently being planned for late October. Using these extended drive tests, we can determine the effect our system has on the accuracy of our simulation results. And finally, as a contingency plan for if we need to demonstrate the system without having full access to the solar car, we can use our measurement unit board with aforementioned spare solar modules and use an Arduino and a laptop to stand in for the vehicle side of the telemetry system.
So this is the timeline of this project. As the project is already listed in a table, I'm not going into more detail about it, but I want to point out several points on this timetable. First of all, we have a very aggressive PCB design timeframe. We only have 1 week for that. The reason for that is there will be some waiting time for the board from the manufacturer and also the components from the vendor to be available to us. By week 4, we should be able to have hands on all the parts we need and then begin to assemble the PCB and begin the testing firmware. By week 5, we should finish integration into the telemetry system, and we're able to capture some raw solar cell measurement in InfluxDB.
There are several avenues for future work that will build upon this project. First, it will be useful to further automate and automatically refine other components of our simulation models in response to the measured data, but doing so beyond the solar array performance, we're considering to be out of scope for this project. Additionally, the fact that SRSim, the simulator, is written in MATLAB complicates integrating it with our other services and data collection infrastructure. There are ongoing efforts to address this, and in turn, this may motivate changes to our solar cell measurement system in the future. It would also be a good idea for us to revisit some of our choices in the PCB design, which we made for the purposes of having a working prototype fast. The design trade-offs will be quite different if we decide to install about 18 of these boards into the solar car. Due to this number that we will need to measure the full array, a more precise analysis of how much power they consume would be quite beneficial. Additionally, our choice of the NRF sock will reduce the time to having a working prototype, but sticking with it long-term would introduce a new toolchain and programming environment into the team's firmware development. That doesn't necessarily require us to choose something different, but it does merit consideration.
Within the scope of this project, the deliverables will be the schematic and the board design files for the PCB. We'll also submit the source code for the telemetry server, the Bluetooth receiver, and also the firmware ran on the NRF52 microcontroller. Apart from that, we'll also submit a presentation and final demonstration of the product, and there will also be a final report submitted. Thank you.